Hello friends, welcome to Learners Forum. So last video was about the parameters of half-wave rectifier. In continuation with that, let us see the next parameter, which is ripple factor, represented by gamma. So in general, the output of half-wave rectifier is not an actually purely DC value. So as we have seen in the circuit operation itself, we would have got the output as a pulsating DC. That is, instead of a straight line, we would have got it as in this manner, which means we will have a pulse in between, that is a discontinuous signal. So this pulsating DC, in the sense it contains ripples, so that is why we are getting the waveform in this manner. So these ripples contribute to a factor which is called as the ripple factor. So the measurement of ripples in the output with help of some factor is termed as a ripple factor. So in technical terms, this ripple factor is nothing but ratio of RMS value of AC component in the output to average or the DC component in the output. So this is the ratio of ripple factor. So RMS value of AC component, in the sense we will get it as IAC divided by average or DC component in the output, means we will get it as IDC. So we have calculated the value of RMS, which is nothing but the combination of both the AC component and the DC component. So we will get it as square root of IAC square plus IDC square. So we are supposed to calculate the value for what is IAC now. So from this equation, we can get the value of IAC as square root of IRMS square minus IDC square. So we can substitute this value of IAC in our ripple factor equation divided by the value of IDC. So this will be the ripple factor RF, that is gamma, which is equal to square root of IRMS square minus IDC square divided by IDC. So we have IDC both in numerator and denominator. So we can combine these two terms and make the value of ripple factor in an even more simplified way. So we will get it as IRMS by IDC the whole square minus 1 the whole square root. So this is for a general ripple factor calculation value, and this is the equation for general circuit. Now let us calculate this ripple factor in particular for a half wave rectifier. So for a half wave circuit, we have calculated the RMS value, which is IRMS is equal to IM by 2, and we have calculated the DC component in output as well, that is IDC, which is equal to IM by pi. So in the equation of ripple factor, we can substitute for IRMS and IDC prescribed for half wave circuit condition. So substituting that, we will get it as gamma, which is equal to square root of, instead of IRMS, IM by 2 the whole square, and instead of IDC it is IM by pi the whole square minus 1. So this IM square will get cancelled, and the remaining value will be square root of pi square by 4 minus 1, which is square root of 1.46. So after taking square root, we will get it as 1.211. That is, ripple content in the output is 1.22 times of DC component. So this is the actual particular value for a half wave rectifier. So this value of ripple factor can be minimized by using filter circuits along with the rectifiers. So this is the concept about ripple factor in general and in the half wave rectifier circuit. Next parameter, load current. So IL can be represented in terms of Fourier series equation as Im into 1 by pi plus 1 by 2 sin omega t minus 2 by 3 pi cos 2 omega t minus 2 by 15 pi cos 4 omega t. So after expanding this, we will get the equation in this way. So here, after combining, we can segregate each term in terms of the respective values. So the first term, 1 by pi, is a constant value. We do not have any time oriented parameter or frequency oriented parameter over here, which is a constant value. So this value is called as average or DC value of load current. In the second term, starting with 1 by 2 sin omega t, here we have the time oriented parameter and the frequency as well, that is angular frequency. So this very first term, which is dependent on time, will contribute to what is called as the fundamental component of current. And after this particular term, everything will be with respect to the base term, that is, this will be the base for all the other terms in the further equation. So the second term, minus 2 by 3 pi cos 2 omega t, will represent what is called as the harmonics. Harmonics in the sense which is derived from the fundamental components. So all the remaining terms will be the harmonic components, whereas this first term will represent the fundamental term and the constant term will represent the average or DC value of load current. So ripple in the output, in the sense it is due to the fundamental and harmonic components, because here only we have both the frequency and time oriented parameters. So whenever we have ripples in the output, it is mainly due to these fundamental and harmonic components and not the DC value, because the actual output is supposed to be DC in a half wave rectifier. If we get any other waveform, that is pulsating waveform, along with this DC value, then it means that these are the sinusoidal components available. So because of these components only, we are getting the ripples in the output end of the rectifier. Next is peak inverse voltage, PIV. So the peak voltage across diode in the reverse condition is nothing but this peak inverse voltage. So it occurs at the peak of each negative half cycle of input when the diode is reverse biased. So when we have a waveform in this way, this half represents the negative half cycle of the input. So whenever there is a peak value in the negative half cycle of the input, we will get a corresponding peak voltage with respect to this input, which is called as this peak inverse voltage. So this happens only when the diode is in reverse biased condition. So peak inverse voltage of diode is nothing but the maximum value of secondary voltage, which is ESM. So which can be represented as pi into EDC under the IDC value is 0 condition. Next is transformer utilization factor. So as we have seen in the circuit diagram of the rectifier, we have seen we would have used a step down or stepped up transformer at the initial stage, because with that only we have required the AC voltage which is supplied into the diode. So the ratio of DC power delivered to load to AC power rating of transformer is referred as the transformer utilization factor. So with this parameter, we can identify, that is we can calculate how much percentage of transformer is utilized for this particular half wave rectifier. So let us calculate the individual values of DC power delivered to load first, and second is AC power rating of transformer. Then let us divide it by the two things, so to get the ratio of this transformer utilization factor, and then we can calculate how much percentage of utilization is done here. So AC power rating is nothing but product of voltage ERMS into IRMS. So voltage RMS value is nothing but ESM by root 2, that is secondary voltage, and IRMS is nothing but IM by 2. So here the ERMS value is 1 by root 2 times and IRMS is 1 by 2 times. So this is about the sinusoidal waveform which creates a difference over here. So secondary voltage is nothing but purely sinusoidal waveform. So that is the reason we are getting it as 1 by root 2 times here. Whereas the current is always half sinusoidal over here. So that is the reason we are getting it as 1 by 2 times of RMS value. So multiplying these two things, we will get it as ESM into IM divided by 2 root 2, which is AC power rating. So we have calculated the denominator portion. Now let us calculate the numerator portion, and then we can divide the two things to get the transformer utilization factor. So the DC power delivered to load is nothing but product of ID square into the load resistance RL. We have calculated the value of IDC early itself. So IDC is nothing but IM by pi. Substituting that over here, we will get it as IM by pi the whole square into load resistance RL. So the transformer utilization factor is DC power delivered to load divided by AC power rating. DC power delivered is IM by pi square RL divided by AC power rating is ESM IM divided by 2 root 2. So solving this further, we will get it as TUF is equal to IM square by pi square RL 2 root 2 divided by IM square into RL. So before this calculation, we need to know what is the value of secondary voltage ESM, which is nothing but IM into RL. So here we have neglected the voltage drop across the forward resistance and source resistance. We have discussed about this neglection factor already. So using that, we can get the value for what is the secondary voltage ESM, and after substituting that over here, we will get the resultant value of transformer utilization factor as this way. So here IM square will get cancelled and RL will get cancelled. The remaining value will be 2 root 2 divided by pi square, which is 0.287. So this value of transformer utilization factor is very low, which means the transformer is not fully utilized in a half wave rectifier. So this is how we can calculate the value of TUF, and you can conclude if it is completely utilized or partially utilized for the corresponding circuit.